Okay, so this is our kind of intro to forces review. It's not going to go over everything, obviously, in the forces unit. It's pretty much going to focus in on the stuff that you guys need to know for the quarterly on Friday. So no matter what class you're in, your quarterly is on Friday, and it is 40 minutes. Okay, so first things first, we're going to talk about Newton's laws of motions. Now, you don't necessarily need to memorize these laws word for word. You just need to know in general, what is the first law talking about? What's the second law talking about? What's the third law talking about? Okay. So the first law, oh, and I am sharing my screen, perfect. The first law is considered the law of inertia. So keep in mind that inertia is just a thing, it's not a force. So if you were to say something like the force of inertia, that is incorrect. Okay, so we shouldn't be confusing inertia as a force. Okay, so what that first law states is that objects tend to remain at rest or move at some constant velocity. So that's what our objects want to do. And they're going to continue to do that until some net external force comes along and acts on them. So that could be like a hit from a baseball bat, or it could be, you know, a push from a person. So keep in mind that whether we're at a constant, that's not how you spell constant, whether we're at a constant velocity or whether we're at rest, our acceleration, and I'm going to specifically say our acceleration in that direction, since we kind of separate our directions into X and Y. So if we're at a constant velocity or at rest, our acceleration in that direction is going to be a 0, which remember means that we have a net force of 0. Okay? That's pretty much what this first law is saying. My cats are fighting. Basically that if an object is at rest or if it's at a constant velocity, then the net force has to be 0. Okay? So a common misconception is students will say, but why does a block or a box slow down if I stop pushing on it? There are no forces. So the tricky thing here is to remember that just because you stopped pushing on the object doesn't mean that there's no forces acting on the object. True, you have stopped acting on that object and you have stopped exerting a force on that object, but there is still one really, really important force acting on that object, which is causing that force to slow, or that box to slow down. And that, of course, is friction. Okay, so there's still friction acting on that object, even though you've stopped pushing on it. So that's why the object slows down. And then another really common misconception is if something is moving, there must be some sort of force acting on it currently. And that, again, is not true. Okay, just because something is moving doesn't mean that there are any forces acting on that object. And when I'm saying like moving, I'm talking a horizontal motion. Okay, so one example might be a hockey puck that's sliding across the ice at some constant velocity. Okay, as that puck slides across the ice is relatively frictionless. Okay, so I can say my mu value is 0. So there is not any forces acting on that object. That object just continues to keep going because there's nothing to slow it down. True, at some point in time earlier on, maybe before this snapshot was taken, some force had to get that object moving. Okay, but moving objects don't necessarily need forces acting on them. Yes, they may have needed a force at one point in time to get them moving, but not currently. So I usually say to think about astronauts in space for this law, not boxes sliding. Okay. So astronauts in space are a really great example because we haven't, or astronauts in space don't really have any net forces. So like, you know, the ending scene in Gravity, sorry to ruin it for you, but like, you know, you push off of something, like, yes, you've exerted a force initially, but afterwards there's nothing to slow you down. So you're just going to keep going. And somebody had asked me to talk about mu. This mu is the coefficient of friction. It just tells how sticky the surfaces are. The actual equation for friction, and I'm going to talk about this a little bit more later, but the actual equation for friction is not going to be on this exam, just like the ideas of friction. So that mu value or that coefficient of friction isn't going to show up on this test. All right, so then we get to the second law, and the second law is really the net force equation. So it's the idea that the net force, which I usually write as sigma F, equals the mass times the acceleration. But of course, we know force is a vector, so really this kind of turns into two equations for us. We have a net force in the x direction, giving us some x direction acceleration. And then we have a net force in the y direction, possibly giving us some y direction acceleration. Okay. Now this left-hand side here comes from our free body diagrams. So we can figure out what to put in for the net force on the x direction and what to put in for the net force on the y direction based on our free body diagram. So let's do some examples. So here we have a box being applied, or with an applied force F, and I have written here that mu k is greater than 0. That just means that there is friction on this surface, so I'm going to need to make sure to include that on my free body diagram. So for this object, it's pretty obvious that there is some applied force. Students usually have no problem getting that part. Okay? They also usually have no problem getting the force of gravity. Okay? Remember, force of gravity always acts straight down. And the force of gravity can always be calculated by doing the mass of the system or the mass of the object times the acceleration due to gravity. Okay? And then we have that upward normal force. And remember, the normal force is always perpendicular to the surface, and it's just kind of like an upward support force. And then backwards, we have the force of friction. Okay? So I usually highlight my free body diagrams, and I usually highlight anything in the like moving direction in green. Sorry, my laptop keeps doing that. And then anything in the non-moving direction in like pink or red. And what I've highlighted is essentially what my equations are going to become. So my net force equation in the y direction is going to look like, well, I'm going to say that up is positive and right is positive. So it's going to look like Fn plus a negative Fg. Now my acceleration in the y direction, this box isn't jumping off the surface or crashing through the surface. So this acceleration is going to be 0, which means this whole side of the equation can become 0. So this really ends up looking like Fn minus Fg. And what that tells me is that my normal force is equal to the force of gravity, or mg. Now that might be helpful, it might not be, but it's good to know. Then in the x direction, right, where I have highlighted green, I have my applied force pointing to the right and my friction point force pointing to the left. So there's my net force equation for the x direction. And from there, I might be able to find acceleration or the applied force if I knew the force of friction, just a bunch of different things. So that's kind of how we would treat one object. Where things get a little bit more complicated is where we have multiple objects. So here I'm saying that this is a frictionless system. So if I was to draw the free body diagram for each of these masses independently, this first mass here, which I'll call mass A, and the second mass I'll call mass B, just to clarify some stuff. Mass A has a force of gravity, as does mass B. And since their masses are the same, their forces of gravity would be the same. And I have an upward normal force on both. And then I have this string in between my two masses, which means there's a tension force acting on each of the mass. So the tension force acts in the direction of the string. So on mass M, or mass A, since the string is acting on the right-hand side of the block, the tension is going to pull to the right. And on B, since the string is on the left-hand side of the block, the tension is going to act to the left. Okay. Now, these tension forces, because they're a part of the same string, are actually equal in magnitude. They're just opposite in directions. And then B has an applied force F. And somebody asked, is there going to be questions on the exam with the normal force and the force of gravity not being equal? So remember, the force of gravity and the normal force are equal as long as they're the only two forces in the y direction. Where things get a little bit tricky is if our applied force is at some angle, because then there's a y component. So that isn't going to be on the test on Friday, but it will be on the kind of bigger forces test. So that we will need to know that information, just not for Friday. So those are my individual free body diagrams, which are great to have. But for problems with multiple objects, we really like to define our system a little bit better. So instead of looking at each individual object, we kind of want to look at both objects as a whole. Okay, so I'm going to just kind of redraw this. And since both objects are in that system, that yellow highlighted string actually disappears. So my mass has kind of come together like that. Okay. So here, A and B, I was defining my systems as the individual boxes, which is why I include tension. Now, when I have my big system as boxes A and B together, tension is now considered internal to the system. So those tension forces don't need to be included on this free body diagram. All that needs to be included on this free body diagram is a big FG for both masses, a big normal force for both masses, and that applied force. Okay. Because I've redefined my system, again, my tension forces are now considered internal to the system, so they don't show up on my free body diagram. So my new free body diagram here allows me to kind of better define my net force equations because I don't have to worry about that tension. Okay, so my net force equation in the y direction, again, equals 0 because there's no acceleration in the y direction. So again, we're seeing that a normal force is going to be equal to a force of gravity. But since this is the force of gravity for the entire two mass system, that force of gravity is going to be 2 mg, since my total mass is 2m. Then in the x direction, the only force that really is going to affect the acceleration of the system is that applied force F. So those tension forces are actually not going to affect the acceleration of the system. Only that applied force is. So that applied force ends up equaling, now remember, this mass is the mass of the system. And since we've defined our system as both boxes, our mass is going to be m plus m, which is really just 2m. So we could use this to figure out accelerations or things like this. So I have a question asking how I did the red equation. So these equations here. So these red equations are based off of this larger system where I'm not looking at the boxes individually. I'm looking at the boxes as a whole. So when I look at the two boxes as a whole, the two tension forces between the boxes end up going away. And the only external force in the x direction is that applied force F. So horizontally, the only forces that I have are the normal forces and the force of gravity. Oh, sorry, that's vertically. And then horizontally, I have this applied force F. Okay. Again, I'm going to say that up is positive and to the right is positive. So in the y direction, again, these boxes are not accelerating off the surface, they're crashing through the surface. So I can say that my acceleration is 0 in the y direction, which means my equation looks like a normal force upward, that's why it's positive, minus a force of gravity downwards. That's subtraction taking into account the force of gravity being in the negative direction. Okay? So if those two things equal 0, then that must mean they equal each other. The force of gravity is the force of gravity acting on the whole system. Since there's 2 m masses in my system, my force of gravity is really m plus m times g, which is the same thing as 2m g. And then in the x direction, the only force acting in the x direction is that applied force F. And again, my mass is the mass of the whole system, so m plus m, and that is 2ma. Then I have a question. Why is the force of gravity 2m, but the normal force is not? The normal force, oh, like why didn't I label it 2m? Because I just forgot to label that 2m, but this would be the normal force for both 2m masses. And then I have a question. Can a free body diagram for only A have a force pulling even though it's pulling on B? No. So this applied force would only show up on an individual free body diagram for block B, since that's the object that force is acting on. A definitely feels an effect of force F, but that effect is felt through this tension force. So that's kind of how we take that into account. So we shouldn't, on a free body diagram for just A, have a force F. There'd only be that tension force. All right. Moving on to a slightly more complicated example of a 2-mass system where we have one object on a table and one object hanging down. Okay, so let's call this A and let's call this B. Okay, and again, I have my mu k is greater than 0, which means that there is friction. So if I was to draw the free body diagrams for those objects individually, my free body diagram for A, which is the block on the table, would have a force of gravity and a normal force. Actually, let me label this F and A and FGA. And then there's this string here, right? On the right-hand side of the block. So that means this object is getting pulled with a tension force to the right. And I can assume that this entire system, right, this block moves this way, this block moves down. So since block A is moving to the right, that means that friction is going to act to the left. Then acting on block B, I have a force of gravity and a tension force. Block B is hanging in the air. So since block B is not on a surface, I shouldn't see any sort of normal force or friction force. Okay. Now, what gets confusing about looking at these two boxes as individual systems is box A is moving to the right and box B is moving down, which makes things really weird because we have two different directions of motion. So what I've talked about before is instead of looking at the individual boxes, look at both boxes as a whole. So we're going to redefine our system as boxes A and B. But not only are we going to redefine our system, we're also going to straighten out our system. So instead of our system having this kind of like L shape that the dotted line is making right now, we're going to say, all right, let's make our system, everything move in a straight line. So basically what we're going to do is we're going to take that 3M block that's hanging down and all of the forces acting on that block, and we're just, for the sake of making our lives easier, going to rotate it 90 degrees. Okay, so and then this is going to be 3M. Okay, we're just going to rotate it 90 degrees. So now that my system is both boxes, both of my tension forces are now internal. So I'm not going to include them on the free body diagram for this larger system. Okay. So acting on this larger system, ignoring those two tension forces, I have a downward force of gravity, but that's the force of gravity A. And I have an upward normal force that acts on A. Now, if you remember, I said when we rotate our, oh, I don't think I can rotate these. That would be cool. When we rotate our box to make our system straight, we also rotate the free body diagram. So we're also going to take this free body diagram for B and rotate it 90 degrees. So that means we have a rightward FGB, and the only other force that I need to take into account, since those tension forces are internal, is a leftward friction force. And I should really say that this is on block A. So now that everything is moving in the same direction, specifically everything is accelerating rightwards, my net force equations become a little bit easier because I now see that the force of gravity acting on B and the friction force acting on A are going to affect the acceleration of the system, whereas the normal force on A and the force of gravity on A are not. Okay. So just like we've done before, we can write out net forces equations for the X and Y direction of this larger system. So in the Y direction, I have a normal force acting on A minus a force of gravity acting on A, and that all equals 0 because the system is not moving in that direction. I don't know where that came from. Okay. So what this tells me is that my normal force on A is equal to the force of gravity on A. Now, A has a mass of M, so this just equals mg. Now, because we're not dealing with the actual equation for the force of friction, knowing this normal force isn't really useful to us. But once we get into actually calculating forces of friction, that's when normal force does become useful. And then we have the net force on the X direction, which is that green highlighted direction. And I have a force of gravity acting on block B minus the force of friction. And this M here, remember, is the total mass of the system. So M plus 3M, which is 4MA. So FGB is really going to be 3mg, force of friction, 4MA. So this equation would be really useful if I needed to find the acceleration. Now you might be thinking, Narc, what the heck do I do if I need to find a tension? You told me the tension disappears in this system. How is that useful? Well, if we need to find the tension, then we just go back to one of our individual force or in our individual block systems where the tension actually is included. So once we have that acceleration here, we can go back and using either block A or block B, find the tension. So for example, if I was to use block B, right, the net force in the Y direction, since B is moving vertically, I'm going to say that down is positive, would look like FGB minus the tension force is equal to MA, and whatever A that I get down here is going to be the same A as up here. So if I get an equation for A, I can substitute it in, and then I can solve for tension. All right, now on to Newton's third law. So Newton's third law says, or really deals with force pairs. So Newton's third law says that in any interaction between two objects, the two objects exert forces on each other. So if our two objects are A and B, this says that A exerts a force on B and B exerts a force on A. The tricky part is realizing that those forces are always equal in magnitude but opposite in direction, always and forever. So some things that are not going to affect this force. Mass differences, meaning it doesn't matter if A is greater than B or if B is greater than A, they still exert the same force. It doesn't matter direction of motion, right? It doesn't matter if they're heading towards each other or if they like come up on each other. It doesn't matter. The forces in the collision are still the same, or the forces in the interaction are still the same. And it doesn't matter the velocity of the two objects. It doesn't matter if they're moving at really fast speeds. It doesn't matter if one is at rest and one comes up behind it, smacks the heck out of it. Doesn't matter. Forces are still the same. It doesn't matter if the size is different. Like, let's say A is super teeny tiny and B is really, really big. They still exert equal and opposite forces on each other. Damage. It doesn't matter if one object gets super damaged in that interaction and the other object doesn't. The forces between them are still exactly the same. So things that will not affect this force pair, everything will not affect this force pair. It doesn't matter any sort of differences in the interaction. Those forces are always and forever the same. Okay. So some people think, or they might think like, oh, well, like, when a smart car and a semi collide, the smart car gets damaged, so it must have felt a larger force. Really common misconception, but that is wrong. Okay. The force of the semi on the car is equal to the force of the car on the semi. Okay. Where the differences actually occur is not in the force, but rather in the acceleration. The other cat wants to join now. Okay. So the semi has a very, very large mass compared to the smart car. Because the semi has a very, very large mass and it feels the same force, the acceleration of the semi is going to be very, very small compared to the acceleration of the car. Okay. This large acceleration is what causes the damage. Okay, it's the same reason why when you punch a wall, the wall doesn't get damaged, your hand does, because your hand feels an equal force, but because your hand is so much less massive, it'd be weird if you had a hand the same mass of a wall. But because your hand has so much less mass, it feels such a larger acceleration, and that acceleration, that really big change in velocity over time, that's what causes bones to break. That's what causes damage. So don't confuse damage with force. Damage actually comes from acceleration. Okay. So another really common misconception that students have is they think that the normal force and the force of gravity are force pairs because they're equal and opposite. So this really comes up when we have a box sitting on a table and students see a free body diagram that looks something like this, and they're able to recognize that the normal force and the force of gravity are equal. So it is true that they are equal in magnitude but opposite in the directions, but they are not force pairs. The reason why is because they act on the same object. We just saw in our definition of Newton's third law that if A exerts a force on B, then B exerts a force on A. This free body diagram is only for mass M, so there's only object A. There's no other object. Okay? So let's talk about it. Let's talk about what would be the force pair situation for the force of gravity. So we know that the force of gravity occurs because the Earth pulls down on the box. So the force pair to that would be the box pulls up on the Earth. Okay. So what that would look like, the diagram for that would look like this. We'd have to have two different objects in our diagram. Okay? The normal force. Okay? The normal force comes from the table pushing up on the box. So the force pair to that is the box pushing down on the table. So if this is our box and that dashed line represents the table, we have this normal force upwards from the table. So if I was to draw a free body diagram for the table, I would have an equal in magnitude but opposite in direction normal force pointing downward, okay? Where the forces that I've drawn, I think my arrows are a little bit different, but those forces are all equal to each other. All right, so that's Newton's third law. Then we're going to get into friction. So like I said, we're going to talk about friction in a very conceptual sense, not in an equation sense. So friction opposes sliding motion, and I want to add that this is a force from the surface. So yes, if a surface exerts a friction force on the box exerts a friction force on the surface. Okay? It's not really going to come up, but it's a good thing to know. Okay? So we have two major kinds of friction. Both kinds of friction oppose sliding. Okay? The first kind of friction is static. So static friction opposes sliding to keep an object at rest relative to a surface. So what that means is the box is not going to slide across the surface. The box is going to remain at rest on the surface. Okay? And this static force of friction can actually be the reason that some objects accelerate. Okay? And this static force of friction acts opposite in the direction the object would slide. Okay? So, for example, let's say I have a cart with some sort of box on top of it, and the cart and the box are accelerating to the right, but the box is not sliding relative to the cart. So pretty much any moving cart ever. If I was to draw a free body diagram for the box, I would quickly be able to fill in a normal force and the force of gravity. What would be tricky is the direction of my force of friction. Now, if I think about it, if this block or box was going to slide, the box would slide to the left. So that means friction needs to act to the right. So my net force equations, and there's no other forces acting on it. There's not like an applied force on the box or anything. There's just friction. So my net force in the y direction still tells me that my normal force is equal to the force of gravity. But in the x direction, what we end up seeing is that friction force, that static friction force, is what's responsible for accelerating that box. So that static friction force is what's responsible for keeping that box on the cart and accelerating the box along with the cart. So the same sort of thing is happening with the mouse in my hand right now. My hand is acting like the cart, the mouse is acting like the box. There's a static force of friction between the mouse and my hand, and that static force of friction brings the mouse along with my hand. Okay. Now, this statement here is true until some maximum acceleration. Okay. There's very clearly a point where I pull my hand back too fast and static friction can't keep up. Okay. I overcome the static force of friction, and my mouse ends up flying all over the place. Okay? So that static force of friction increases with the acceleration until some like break free point. A similar time when we might use static friction is when an object is at rest on a surface, but there is still a force being applied to it. Okay? So my free body diagram for this box, again, we'd quickly be able to draw normal force, force of gravity, and applied force. What students might forget, though, is that because this is at rest, there has to be some leftward force as well. And that leftward force is the static force of friction. So the y direction is exactly the same as it's pretty much always been through this video. But the x direction because we're at rest, my acceleration is 0. And what that tells me in the x direction is that my applied force is equal to my static friction force. Again, though, this is until some maximum applied force. All right, so the static force of friction will increase with the applied force until that same break free point. So the static friction force has the ability to vary based on the situation, and then it'll vary, it'll increase until we get to some like maximum value, and then we start to slide across the surface. Once we start sliding across the surface, that's when we start to deal with the kinetic force of friction. Okay. So the kinetic force of friction opposes sliding when two objects slide relative to each other. So like this, right? There's sliding motion between the two things. Okay, so anytime a box is sliding across any surface, you're dealing with kinetic friction. Okay. Kinetic friction always acts opposite the direction of the sliding. So if we're sliding to the right, friction acts left. If we're sliding left, friction acts right. If we're sliding up, friction acts down. If we're sliding down, friction acts up, and so on. Okay. Friction, or kinetic friction, unlike the static force of friction, is always some constant value. So it doesn't increase or decrease depending on like the speed or the applied force. It's always some constant value. And that constant value is less than whatever the maximum static force of friction is. Not really something that we need to use ever, but is a good point to know. Okay. So we're going to take a look at two different situations here and just talk about the direction of friction and kind of how that affects the velocity. So here I have a box with an applied force to the right, but the box is moving to the left. This is Tesla. She likes to interrupt physics. Okay. So my free body diagram doesn't depend on that direction of motion at all. My free body diagram only depends on the forces acting on the object. So my applied force is to the right. Since I am moving left, friction also needs to act to the right, specifically kinetic friction. Okay. My y direction is exactly the same as it has been. So we're just going to take a look at the x direction. Okay. So let's say that to the right is positive, which means that this object starts with some negative velocity. So if to the right is positive, then that applied force and the force of kinetic friction add together to give me my net force. Okay. So then I want to think, okay, based on that, will the object increase in velocity, decrease in velocity, or have constant velocity? Okay. And the answer here is that the object is going to decrease in velocity. And the reason being is because the net force and therefore the acceleration are directed opposite of the velocity. And we know from the last unit that anytime the acceleration and the velocity are in opposite directions, the object is going to slow down. Okay? Keep in mind that net force and acceleration share a direction. So if the net force is right, the acceleration is to the right. All right, then another example would be pretty much the same thing, but now our box is moving to the right. Again, that really doesn't affect much of our free body diagram. What that direction of motion is actually going to change is the direction of friction. So if our box is sliding to the right, then that means friction acts to the left. So now our net force equation isn't the two forces added together, it's the two forces subtracted. Now the values of these forces from one situation to another, let's say, hasn't changed. So what we're going to see now is we'll still have a net force to the right, but because I'm now subtracting the force of friction instead of adding it, I have less force, which means I have less acceleration. That's just a fun fact. Okay? Just like we did before, I want to know, will this box increase in velocity, decrease in velocity, or have a constant velocity? And this time, since my net force is still directed right and my velocity is directed to the right, this object is going to speed up. Right? Again, because net force, acceleration, and velocity are in the same direction. All right, so that direction of motion can affect that direction of kinetic friction. So just make sure you're paying attention to that. And that is pretty much everything that I wanted to go over. And let's just take a few seconds. If you have any lingering questions, feel free to ask them in the chat. We'll kind of do like a question and answer in the chat. So we got asked, will tension be a big focus on the exam? Being that there's only 2 questions, no, like it might be one part of one question, but it's not like there's going to be an entire question on it. Oh, okay, I got a question to go over elevator scale readings. Okay, so let's say we have a person standing on a scale in an elevator. Okay. So the free body diagram for the person is always going to look like a force of gravity downwards and a force from the scale upwards. Now that force from the scale is really just whatever the scale is reading, and could also be considered a normal force. Okay. So if our net force is 0, meaning we're moving at a constant velocity, or we have we're at rest, the normal force is going to equal the force of gravity. If we are accelerating upwards, then the normal force and therefore the scale reading is greater than the force of gravity, because in order to accelerate upwards, the upward force has to be larger than the downward force. If we are accelerating downwards, the normal force is going to be less than the force of gravity, because if we're accelerating down, then our net force is down. So the larger force has to be Fg. Now, Fg is the same in every single one of these situations. Fg is always the constant value. It's the normal force that's changing. Okay. Now, notice how I didn't talk about direction of motion at all. It doesn't matter whether the elevator is moving up or moving down. What matters is the direction of the acceleration. And then I had a question about how much of the quarterly is going to be forces. So it's going to be half and half. Like one question will be kinematics and then another question will be forces. So it's not like the whole test is going to be forces. I just went over forces today because we didn't have time in class to do a traditional review day, kind of like we did with kinematics. Is there a formula for the net force equation? Is net force of y always equal to MAY is always equal to 0? Pretty much yes, for most of the stuff that we do, because most of our objects are objects on horizontal surfaces, which means they're not accelerating vertically at all. They're only accelerating, if they are at all, horizontally, which means that the net force in the y direction does often end up being 0. For this part of the forces unit, we're only really dealing with the normal force and the force of gravity in the y direction. As we move into kind of more complex problems, and I went over this with you guys yesterday, but when we start to pull at angles, our net force in the y direction still might be 0, but now we have some additional y component of that tension force. So that's when we, have the normal force not equaling 0. the only time we're really going to have an acceleration in the y direction is if an object is accelerating upwards or accelerating downwards. The quarterly is Friday. Somebody asked what type of kinematic equation questions are going to be on the test. You might need to use all of them or one of them. I can't be that specific. What equation would you use to find the tension force? So let me go back to the half-Atwood machine example. So here, let's say we wanted to find the tension in the string acting on B. So keep in mind that the tension is the same whether we are using object A or object B. So it doesn't matter which object we kind of look at to determine the tension. But when we're determining the tension, we want to make sure that we're looking at the objects individually so that tension is an external force. So the tension acting on object B would be FGB minus FT equals MA. So we would add tension to both sides, then subtract MA. So this would be FGB minus MA is the tension. FGB in this equation, it's 3M. So this would be 3mg minus MA equals FT. And then if we knew A, that equation would be perfectly fine. But if we didn't know A, then we would need to sub in probably the equation we previously found for A. So it might be like part 1 is find the acceleration of the system. Part B is find the tension. The question was asked, can we use our notes or is this open notes? Yes to both questions. You can use your notes. It is open notes, just so it's fair between people in class and people at home. But like I've said before, just because it's open note does not mean it is open friend. It is open notes, not open friends. It is very easy for us to tell when people have the same answers. We're not stupid. So don't cheat, is basically what I'm saying. Other questions? Okay, if you have further questions on anything we covered, make sure to ask Mr. Warner or I tomorrow. That's why we said the test was Friday instead of Thursday. That way you guys can ask questions on Thursday if you need to after studying. Today, if you have questions as you're going through, my kids, you guys are welcome to remind message me or Canvas message me. Warner's friends, of course, you guys can reach out to him. So we're going to go ahead and end this for today. Thank you guys for stopping by. I was really happy to see how many people we had joining. Have a great rest of your day off. I know it's kind of rainy, which sucks, but at least it's a day off. Bye, guys.